This week's big shift is that embodied AI is starting to look less like collect more robot data and more like learn from human motion at scale, then adapt efficiently. One line of work shows you can cut control latency from tens of milliseconds to real time while keeping long horizon planning intact. Another shows human grasping data can outperform classic robot-centric supervision. And a third suggests egocentric human video may actually be the better pre-training substrate than teleoperated robots. The common thread is simple. Human data is becoming the new backbone of robotics. Let's explore the first paper. AHA-WAM Asynchronous Horizon Adaptive World Action Modeling with Observation-Guided Context Routing. AHA-WAM from Shanghai Jiao Tong University, Shanghai AI Laboratory, Baidu AI Cloud, and the University of Hong Kong reframes world action modeling for robot manipulation as an asynchronous 2-timescale system. A low-frequency video DAI-T acts as a long-horizon world planner, while a high-frequency action DAI-T runs closed-loop control on short action chunks. Its key novelty is observation-guided video context routing, which uses the latest visual observation to adapt cached planner context without rerunning the video model, plus horizon adaptive offset training that makes the action policy robust to planner executor phase misalignment. Built on 1.2.5b and trained without robot data pre-training, the system reaches 92.8% average success on RoboTwin, 2 across 50 tasks, and 78.3% success on 4 real-world bimanual tasks, outperforming FastWAM and matching or exceeding strong VLA baselines in deployment. The asynchronous schedule also raises closed-loop control from 5.26 Hz to 24.17 Hz with 41.37 milliseconds latency, and the distilled AHA WAM flash variant pushes this to 56.95 Hz at 17.56 milliseconds, showing that long horizon visual dynamics can be retained while sharply reducing control latency. Let's explore the second paper, Human Universal Grasping. Human Universal Grasping, or HUG, from New York University, Tsinghua University, the University of Michigan, and Meta Reality Labs Project ARIA team reframes dexterous grasp learning around human data instead of robot teleoperation or simulation. The system is trained on 1M, HUG-S, a 1M frame egocentric dataset collected with ARIA Gen 2 smart glasses across 6,707 recordings in 41 buildings, then learns a flow matching transformer that fuses RGBD with a query 3D object point to predict a 9-dimensional manograsp state, wrist translation, 6D wrist rotation, and kinds joint rotation. HUG-B ENCH standardizes evaluation with 90 unseen objects spanning 5 geometry classes and 3 size bins, reconstructed into metric scale meshes for both simulation and real robot trials. In Mujoko, the full RGB plus PC model reaches 73% success on the test split, with 14.6 millimeters fingertip contact error, while an Oracle replay of recorded human grasps reaches 94% and 7.4 millimeters. The key ablation shows that removing the 3D supervision drops test success to 32.7%, and removing RGB drops the model to 70.7%, confirming that geometry and semantics are complementary. In real-world tabletop trials on 30 unseen objects, HUG achieves 66.7% success, outperforming DEX 1B at 43.7% and CAP at 32.7%, and it still reaches 62% in an uncontrolled in-the-wild household setting after zero-shot retargeting to the ability hand and Wuji hand without per-hand training. Let's explore the third paper. Human-scale, egocentric, human video can outperform real robot data for embodied pre-training. Human-scale from PKU, NUS, MIT, UCSB, and NVIDIA tests a simple but consequential question for embodied pre-training. Can egocentric human video beat teleoperated robot data when both are matched for scale? Using the same autoregressive world action model built on WAN 2.2 with a mixture of transformers architecture, the authors pre-train on 5,000 hours of curated human-net egocentric video or 5,000 hours of real robot trajectories, then post-train on the same 1,500 trajectory Agibot world manipulation, set and evaluate on held-out seen and unseen tasks. The result is that human video not only scales cleanly, but generalizes better. Validation action loss falls from 0.008 to 0.0067 on seen tasks, and from 0.0234 to 0.0204 on unseen tasks. As egocentric pretraining grows from 100 to 5,000 hours following a strong log linear law, while matched robot pretraining stalls on unseen tasks near 0.0254. Relative to no pretraining, egocentric data yields a 35% lower scene loss and 24% lower unseen loss. Compared with robot pretraining at 5,000 hours, it is about 20% better on unseen tasks. The strongest evidence comes in real robot rollouts on an Agibot bimanual platform. The egocentric pre-trained policy reaches 92.5% success in distribution and 90% out of distribution, whereas the no pre-training baseline collapses from 40% to 0%. The paper's core claim is that egocentric video supplies the coverage and diversity needed for pre-training, while a small amount of robot data is sufficient later to close the embodiment gap. That's a wrap on today's AI paper highlights. Thanks for watching.